Okay, so this work that I'm presenting, actually, I'm using the template from my university, but I do it as a consulting gig. And the idea is to be able to run large-scale system simulations using FMUs for this specific type of inverter. It's called a grid-format inverter. I'll tell you a little bit about the background, about this library that I have to develop myself, how we had to do FMU expert for a specific simulation tool and why we had to use that simulation tool. I'll give you an example and the options that we had. Before I go into details, there's in my field, in the power grid field, and power electronics too, there's been all this hype about grid-forming converters. And grid-forming converter is nothing else than you see this, this would be the picture of the converter. So it's something called a multi-modular converter versus voltage source converters. And basically what that allows you to do is that if you control them in a certain way, you can reproduce the sinusoid that you have to inject in the network. And it has a little bit more of controllability. And so in the what you will see inside of these things is that you have to take some measurements, and then you have different cascading control loops until you arrive to the PWM. Now, simulating this for large system simulations, it's quite a challenge for domain-specific tools that have been built to do that. I don't know how fair, well, Modelica tools would do okay anyway, but basically when you're talking about having many of these models, it becomes to be very hard. And so the idea is to represent these models for large-scale simulation with something much more simpler, that is to represent the converter up to this part here, the current loop. You don't really represent it in detail, but you abstract it into a sort of voltage source with that you can manipulate the internal voltage and the frequency. And so that's kind of the idea. And why these grid-forming converters are becoming popular, even though there's none of them in the real world that I know of, is because of renewables. Now, the company that I did this work for is called the New York Power Authority, and they are they're part of the state, New York State. And so in New York State, somebody decided that we should have 70% renewables by 2030. I don't know how, but it's in the law, it's in the climate protection law, and decarbonization by 2040. So I don't know who had this idea, but basically to be able to do this, there's a lot of challenges in integrating renewable energy resources. You have a lot of stability problems, issues with protections. It's really a nightmare. So you gotta do some simulations at least before you try to figure out where you're gonna put them and how much and so on. But it's extremely challenging to conduct simulations if you want to do it for an entire state, at least. So the solution is that New York Power Authority has one of their larger grid models has 500 substations, hundreds of generators. So it's a very large model, but they also need to run it in real time. And the only simulator that they can run that model in real time is this simulator from OPAL-RT. And this modeling environment that they use is called ePHASORSIM. And ePHASORSIM gives you two choices. If you want to add a model that doesn't exist in their library, you can build it in Simulink and then copy-paste how many times you need it, or you provide an FMU and you parameterize it in an Excel file. So they talked to me because doing it with the Simulink thing was a nightmare to add this new model that doesn't exist in their library. So they needed somebody to build that model. And they needed to have a very simple sort of functions that the model can represent. And just so that you get the idea why this is sort of popular right now, or it's becoming popular. So basically, this way of controlling the converter is attempting to making it act like an actual synchronous generator. I mean, so they're trying to make it look like a synchronous machine that is a conventional generator. And what a conventional generator can do is that they can impose the terminal voltage magnitude and the frequency of the waveform and establish an AC network. You cannot do that with existing grid following converters. So a normal PV converter has to look at the terminal voltage and figure out what is the frequency of the grid and synchronize to it before it can connect. So this sort of technology is attractive, and this is the only real world case that I know. It was done by people from RTE, where they did a trial test. This is not still in operation, but you can see here in this picture over there how gradually you're building up the voltage of the point of connection, and you are establishing the frequency at the point of connection. So the ability to form a network is what is actually attractive, especially if you black out and you have to restore the network. If you black out, all of those PVs that are grid following cannot reconnect. You're blacked out. They cannot sync to anything. There's nothing to sync to. Whereas if they have this new approach, they will be able to do this same sort of thing as long as they have enough sun. So this test was for a battery energy system. And I think if you adopt the concept, because this is not a reality yet, the concept is that you put this type of converter technology both in PVs and in wind turbines, you might be able to additionally add other functions to it that will emulate a little bit of inertia. Because right now, with the kind of converters that you have, you basically don't have any inertia. You don't have any of the mimicking of the mass of a generator that can absorb and expel energy to maintain an equilibrium. So that's kind of the concept, right? And the hypothesis, because this is all claims that people goes and makes, but I really doubt that this is true, that you can make this work, is that if you have all of the converters or a large amount of these converters as grid-forming converters, you could operate 100% renewable. And I think that's a little bit silly, but that's where all of this is coming from. So there is no grid-forming model that they could use, so I had to build one. This model is built based on industry standardized descriptions, which is basically a PDF with a bunch of block diagrams, so you gotta figure out to implement that. So you see here at the top in that library that I made for them, you see that there is the component right there. That component, of course, is built in object-oriented fashion. And then I have to generate FMU for that simulator. So you have here a wrapper that I created. And this wrapper needs a bunch of things that are to be able to, so that the FMU can be read by that simulator, because they're doing some weird things. They say that it's FMI, but yeah, it's FMI package, but the way that you have to package it is very specific. Here you see the generator FMU that I have. Then I have models to test the FMU. So here, inside of this, I put it inside of a Modelica plant, I call it, which is basically going to allow me to connect these electrical terminals to a power grid model. I have one for the Modelica model that has been wrapped, and one for the FMU that is inside of that Modelica interface. And then similarly, I have test models for the Modelica only implementation, the Modelica with this sort of causalization interface, and the FMU with an interface to run it in Dymola, because I mean, you can, so the idea was to do all of the testing that I could do as possible before putting another simulator within Dymola. Why? Because running the stuff in that simulator is extremely convoluted, and it takes not only time, but it's very error prone. So I wanted to debug everything in Dymola, and when it was ready, I could test it in the target, and then in the offline mode of the OPAL-RT simulator software, and then in the real-time mode, which is not, I couldn't do that myself because I didn't have access to facilities, all those guys did. So for you to understand, basically you have to build a voltage source model, and in the voltage source model what you're gonna do is that we're gonna have an internal impedance, and if you don't control anything, you have to calculate what is this. And this is important because figuring out this makes it possible to figure out how to initialize correctly a controllable voltage source and then providing all of those initial values back into the controls. So this is how I did this, right? So the terminal voltage is going to be given by this V, angle delta V, and is a complex variable. So you can basically, to calculate the terminal voltage here, you just do Kirchhoff's current law, and you find the real and imaginary expressions. And so these expressions, you can, during initialization, you can actually type the initial equations for, well, yes, it's initial equations, yes? No, actually, these are initialization parameters that I create. And this VR0, IR0, and where is the real and imaginary part, and there's the imaginary voltage, real and imaginary part, magnitude and angle. And these have to be calculated based on all of this data that is provided by the other simulator. The reason is that we do a lot of steady state calculations that have no dynamics involved, which we call a power flow problem. And that helps us provide good start guess data to initialize the dynamics part. So all of these fields that you see here are mandatory fields that are going to be passed by this OPAL-RT simulator. So part type, this is entirely just for their system to work, but you see these parameters are the ones that are required for the correct initialization of everything, basically. Okay, so that's the voltage source, but of course, if I'm going to build this grid-forming converter model, then I need to control it to mimic the two control functionalities that they asked me for. So basically, the basic building block is to make a controllable voltage source, which will have as an outputs the internal voltages, because remember there is an impedance inside of it, both in what's it called? Polar and rectangular coordinates. And here you have inputs that are going to be provided by the controllers in terms of magnitude and angle, because this is very typical the way that we model things in power systems. And so there is this connector that is a mandatory connector from the simulator that they have in their library. You have to put this because they will check the FMU if you were actually using this pin. And this pin is exactly the same as the pin of my library. So in my library, you have the network, OpenIPSL is there, and then I just created an interface bus that's, I have the same variables, so there was not much to do, but you have to do it correctly because of the sign conventions that they have used with the pin. So I have Modelica convention that all the currents come in, and they have a convention for the currents that is pushing out. That is the power system conversion. So that had to be fixed. And so what is left is to link the equations to the pins. So this is a real and imaginary voltages, and I link it to the currents of the pins. But if you do this, you have 4 variables and you're missing 2. Basically, to add the other 2 variables and have the balance model, you have to add active and reactive power equations and link them to the pins. So now, basically, this is a balanced model. But we want to export FMU to work with the other tool, so we need to couple it, and to do this, we're restricted to use FMI version 1. So that's why we have all these reels, and it's because the vendor of that simulator doesn't provide support for anything new. All of these things I had to do because I reverse engineering a tool where they tell people, put your model in here that you want, put these pins, and I will create the FMU, but the tool is not maintained since Daimola 2017 and OpenModelica 1 point whatever, very old. So I have to reverse engineer all the process of how to interface things, basically. Okay, so you could choose for controlling this voltage source. You have to either, you're going to provide a change in the voltage that either that you already know the initial value for everything that is behind, or that you're going to use the initial value that you're provided. And that depends on how you model the controls. Different people want to do it a different way. So here's a simple example. Here is the power network with OpenIPSL. This is this interface, what do we call this? Interface connector that goes from the OPAL-RT pin to OpenIPSL pin. And this is the controllable voltage source. And we just do a very, very silly thing, is to do this large step on the voltage and this angle deviation and see if you can track. These things are extreme examples of variations that you could have, and if you can simulate it. So we run this in Dymola and then in the real-time simulator in ePHASORSIM, and we got the same answer, so we checked that the basic setup was fine. The next step was to add the controller. So the first controller, we call it a PF droop. If you see here, basically it's a gain, which is the droop value, and then basically you're from that, you're going to calculate the angle through this integrator. So that's the droop controller. You take measurements that are, if you take a small deviation approximation, basically you look at the angle difference and you can summarize this in this multiplier, and that's what we implemented in those gains over there. So when you have a deviation in the power, so you have a reference and it moves a little bit from the reference, the signal that comes in there is going to be able to respond so that you change the angular frequency of the internal voltage and you reduce or increase the inverter power by changing the angle. So when you have phasors, you don't model the frequency directly, you model the angle, and the rate of change of the angle gives you the frequency. You don't need to model anything extra, you just have the derivative basically and add it to the steady state. The other thing is that you have to model overload limiters, and this models is basically that standard industry approach, but just implemented in Modelica, where you have an upper and a lower limit that you're implementing. Okay, there's a little problem that I had was I need to have the exact angle that is seen in steady state in the terminal, pass it, and enforce that this is respected at initialization. So I had to use a resettable integrator to be able to fix this. It seems trivial. I couldn't figure out how to do it. It took me 2 months of like, oh, how do I do this? Just thinking. Not just doing that, I did other things. But luckily, the MSL actually has that. In the past, I didn't know that we had it. So we implemented some resettable with somebody else in another work. But you can just use this resettable integrator. And you can get now the steady state and initialization to be always the same that you had as this thing. So there's another control loop. This is called the reactive power to voltage droop. So basically here, if you take a small approximation to reactive power that goes in here, you see that you're going to you can basically calculate out of this product, which this is just a constant parameter. This is the internal voltage, and this is the terminal voltage. So when you put this into here, you have a change in the terminal voltage, and so the droop will manipulate the magnitude of the internal voltage to adjust the reactive power output. You also have limiters for this, and now the additional step is that there are different options on the priority you want to set. If you want to control the reactive power over the voltage magnitude, because you cannot do both things at the same time. So in this world of power systems, I love to use these binary flags that is either 0 or 1. And then you have 2 of them, unfortunately. So here you have 2 flags that allows you to decide if you're going to use the Q reference equal to 0 or you're going to set it equal to a reference value. So that's one flag. And here is another one that is going to deal with the whether or not you're going to apply this PI loop or just limit the voltage. So these are the 4 flags. Basically, I have to test every possible variation where that is seen. And the issue that I had here is that real-time, the simulator from OPAL-RT didn't like in the FMU to have passing of binary values. I don't know why. So I had to convert this thing into real to Boolean block. It was the only way to get it to work with that toolchain. Having said that, everything is built. And this is all the, what do you call this? The battery of tests that I had to do. So I had to test the droops individually, the two loops individually, then the control scheme on its own, then the entire converter put together, all of the variants. And when all the models and features were together, you can compare. So this just gives you an idea of the different variables that had to be built to do all the validation process and so on. So here you can see now in the encapsulated model, which you see this little, well, this is very hard to find. If you see these little assemblies, I call them, right? So it's basically, it has, it's just a block that you drag and drop. But I forgot why I was going to say that. But, oh yeah, when you click on it, you have now all of these parameters to fill out. Some of these parameters up to here are the mandatory parameters from this OPAL-RT simulator, but everything below is all the parameters of the model. And then you have additional parameters due to the limiters that were implemented. Am I done? Okay, 2 minutes? Oh shit, I have to. Okay, the last thing, and this is the kind of the interesting part for most of you, I guess, is that OPAL-RT creates this casualized interface that takes voltages read from their simulator, passes it to this pin, I pass this in here, and then you have to inject currents. So this block over here basically imposes the casualization that you have to inject currents and read voltages. That's how that simulator works. So basically what we do here is that we add the inputs, well, you know, whatever you have in that. I'm just illustrating here with the voltage source that you're going to control, and you have this pin that is connected to it. So with that, you can actually pass to generate the FMU. So you need to actually have WS2 installed to do cross-compilation with Dymola. And these are all of the flags that you have to put in. And this is pretty much why I wrote this paper, so that nobody else has to go through this misery again. Without these flags, it won't work in the other simulator. So I figured, and the way that I found this is that I looked at the debugging logs of their little tool, and suddenly I saw that they have written all of these things from their tool is called the FMU creator, but you need all of this for the FMU to actually be able to run in their system. So it's another tricky thing, but you know, once you set them up, you create a Modelica function that use the code generation and so on. And finally, so here is the ePHASORSIM simulator, which can be run offline or real time with the hardware. To model there, you basically have a spreadsheet with parameters, and you tell them this one goes in this substation and has these parameters, and so on. And so what you're going to do is that you can use many of the same instances of the FMU. You have to first say that it's going to be there, then you start the simulation, and at each iteration, this guy passes the voltage, and you will calculate the current coming back, and you have to request for the value. So that's really high level what it does. Here's a simulation result. So they didn't let me show you the actual model, but for you to have an idea, this is the electrical grid of New York. So all the power here from Niagara Falls and from Canada goes down to fit in New York City. Also other connections here. So it's a large grid model that I have set up, and they have put 9 of these FMUs to run the simulation, and then they have set up a big fault. So they have put those 9 there with this capacity, because here we have the Oswego nuclear complex that some crazy people wants to put it out of operation, and I think, no, you shouldn't do that, right? But you can't convince people of these reasonable things. So they did a simulation of whether or not if you put these 9 converters in the system, if you would be able to maintain stability. And yeah, the answer is yes, if you know where to put stuff, right? So I think I cannot have more time. I should be done, right? Okay. Just to summarize, how you proceed to implement FMUs for specific grid tools really depends on how they do the implementation. And just because they say that they're FMI compliant doesn't mean that is going to work. There's still a lot of things to do. Message sent.